So I'm gonna record this session as always. So I just want to go back and so this is 45 of almost 65, 66. So once again, we were working on the idea of building a confidence interval. So this confidence interval helps me make some inference on what might be a value for mu, even though I don't know mu. So I don't know the population the population mean. I might not know the population proportion, as we noticed last class, and also we might not know the standard deviation or the variance. So so the population standard deviation or variance. So we can use a sample for all these these estimators and create a confidence interval, and I am going to be 90, 95, 99% confident that mu is going to be within those values. So as I mentioned before, we have several cases. The first case that we analyze is to estimate the population mean using the sample statistic X bar. So we have two cases. Remember, we have one case where we know sigma, or we know that our sample size is greater or equal to 30. So in those cases, we can use the C-score, right? So we have another case. So we have another, so this is N, right? So we have another case where N might be less than 30. So we don't know sigma, the only one that we have is S. So we are gonna use the T distribution, right? So those are the two cases, big samples where sigma is known, or it can be a small sample. If we know sigma, we can approximate to the normal distribution. For the second, we have a sample lower than 30, and all we can do is to use the T distribution. So in these two cases, we are estimating the population mean. So we went through this process several times. I showed you how to do it in Excel. I do think that Excel is super easy, and all these things is very important that you know what they mean, and you know how you can find those values, because you can also find if you have the confidence interval and you have other values, you can find the values that you might be asked to do. So in this case, we have so the two of them. So this is when sigma is known. Sigma is known here. Sigma might be not known. In this case, we have a small sample, so we use the T distribution. Also, we learned that when we want to use, so in some cases, you don't know what is the appropriate sample size, you can compute it. So you can use a sample size for convenience. You can say, I want to use a sample size of 50, 30 people, but in order to expand your horizons and to make your study more significant, you might compute the sample size and come up with a sample size that is appropriate for the study, and that will make your results more significant. So so more significant means that you have more leverage to defend your results, saying that they are well, that's the idea of significance. It's not that they are more accurate, but you are setting some parameters, some boundaries that you can say these values approximate to the population values. So we have the T distribution. We also went through the case. Well, for the T distribution, remember, in order to find the C scores or the T scores in this case, we need the level of confidence and the degrees of freedom. So that is very important, because if you are using the tables, you have to know these these degrees of freedom, right? So if you are using Excel, so you can find the margin of error very easily, and just compute the values. But also you have to be sure that you are doing the right thing, because in many cases the question is, what should I use? Should I use the first formula, the second formula? Well, it all depends on what you are doing. As I mentioned before, you have a large sample. When you know sigma, then you can use the confidence interval for the normal distribution. You don't have a big sample, you are using a small sample, then you are gonna use the confidence for the t-distribution. So you need to know exactly what you are doing so you can make the proper call. So in this case, this is very simple to use. So we might have for this population parameter, we just need the sample size, the confidence level. Here we don't need alpha, is asking for the confidence level C. As you can notice here you need the so-called alpha, right? And we know how to compute alpha. So keep that in mind, because in many cases when you are using Excel, you might be asked to use either alpha or the confidence level. So in this case, we are using confidence intervals. The most, if you are doing this by hand, you are going to be using confidence in the confidence level, the C. But when you are using Excel, now you are using alpha, right? Just small things here. This is another type of. So I think I did these two, which are very simple. I just found this information on the internet, and all you need is those values. So I think this one I found it online, and I made it available for students. So today we are going to do the last part. So we are going to use the we are going to build a confidence interval for the standard deviation and the population variance. Okay, so before going there, so we have the sigma. So we know sigma. We use the normal distribution. We don't know sigma, and we have a small sample. We use the t-distribution. So we also have the population proportions. So we are using the point estimate, which is p hat. P hat is the sample proportion, and we are trying to estimate the population proportion. So once again, it's like doing a binomial experiment. So we are going to be approximating this by using the normal distribution, right? So it's very easy. All I need to know is the value of Z, so the C score, and I need to know values for my sample proportions and the probability of success and probability of failure for my sample proportion and the sample size. So we also did this in Excel. All I need is the number of successes, the sample size, and the confidence level. We have these three inputs. We can solve the case very, very easily. So also we mentioned that for both, for the mean and for the population proportion, we can find the number of subjects that we need to conduct a good experiment, right? So in this case, so we have so a formula that is used for finding the sample size in a sample size in for the mean distribution for the population mean. So let me find it. I think so. Somebody was asking me about that. So this is the formula for finding the correct sample size when we are estimating the population mean. But if we are estimating the population proportion and we need to know how many people we need in our experiment, so we are going to use this formula, which is it's almost the same. This is the sample size. The size of the sample is going to be determined by P and Q. the C-score and the margin of error. So I was mentioning that in some cases you don't have any reference. What is the probability of failure? What is the probability of success? You usually you use a value that is 50 and 50%, right? So I don't have any information. I want to know how many people are gonna vote Democrat, how many people are gonna vote Republican in a town that I don't know. Well, my best choice is to assume 50 and 50%. So in this case, we are using the 50 and 50%. So we can compute the sample size, and under those circumstances, I'm gonna need almost 1,068 voters. So if I can pull these numbers, I can make sure that I will know what's going on. So if you saw the elections, in many cases, they don't need a big number to know who's gonna win. I was looking at the results, for example, in New Jersey, with less than 1% of the population in New Jersey. They determined that Vice President Biden was going to win the election, whereas in other places like I think Montana, or I don't know, one of the states in the middle, in the Midwest, they were with very few people. They knew who was going to win the election in that state. So in this case, we don't have any information. We use 50 and 50. But if we have information, we know that 31% of the people are going to vote for that particular party. So we probably might need a little bit less people to account for the value. Okay. So so these formulas are very simple, are very easy to manage, and they are very helpful because once again, convenient samples are effective in some ways. You determine the sample size. You don't need a big sample or a super or a small sample to make some judgment. So in some cases, you want to be more accurate in your results, more certain in your results. So you find the sample size that is going to be very good. So I was mentioning that this part of analysis is called the power analysis, where you are playing with the confidence level. You are determining the sample size and some other things that you need to make your results more significant, right? So you can be more sure that you are making an inference that is more powerful. So that's a big that's a lot of things to know. This idea of power analysis is not that easy. It implies and has a lot of thinking about this. I have seen many software that are used for this particular thing. But anyways, power analysis is something that we need to be aware of because just choosing a sample is not enough. We have to be more accurate in terms of that particular sample. So so that's important. We have two formulas, one for samples when we are estimating the population mean. We have another formula when we are estimating the sample size for population proportions. So today, I think it's going to be very simple. The explanation in the book, very interesting, very like so many steps. So when you see what I have for you in Excel, you're going to almost laugh at how easy it's going to be to compute those values. So once again, all you have to do in all the cases is to identify what is the tool that you need to use, right? So in this case, you are looking for a confidence interval for the standard deviation. Oh, I need to use that tool that I have in this spreadsheet. So in this case, to build confidence intervals for variance and standard deviations, we are going to use a new distribution. So we are familiar with the with the normal distribution and the use of the C-score. We are also now familiar with the t-distribution, which is very similar to the normal distribution. And now we are going to be using what is called the chi-square distribution. Chi is a Greek letter. So it's almost like an X, or this kind of like this, and this is chi-square. So it's not an X, it's something that has a little curve over here. So this chi-square distribution is going to be helpful for us to build this confidence interval. So we can use the point estimate for the variance, using the population variance, using the sample variance, and the point estimate for the standard deviation, the population standard deviation, is going to be the sample standard deviation. So we know that the sigma S squared, which is the sample standard deviation, sample variance, is going to be an unbiased estimate for the population variance. So we have this here. So so we're going to continue. So the chi-square distribution, you can use the chi-square distribution to construct a confidence interval for the variance and the standard deviation. So if the random variable has a normal distribution, then the distribution forms a chi-square distribution for samples of any size n greater than 1. So when we have a sample that is greater than 1, so meaning 2 and more, so we might be able to use the chi-square. Of course, a very small sample might not be the best thing to do. So we are always hoping to have a sample that might be more representative of these values. So I just want to make a quick stop here. I'm gonna go offline because I need to do something very important. So I will be back in 2 minutes. So please wait. I'm gonna stop the video for now, 5 seconds. Sorry for the interruption. I'm not going to tell you what I did, but it was emergency. It was an emergency. So in order to find the chi-square, we have this formula, looks horrible, but basically it's nothing. So the chi-square distribution is going to be the result of n minus 1. So does anybody remember what is n minus 1? And if you say that this is the degrees of freedom, so this is the degree. If you say the degrees of freedom, very good. So you are absolutely right. So we need to identify the degrees of freedom, multiply it by the variance, and divide it for the sample variance, and divided it by the population variance. So that's the idea of the chi-square distribution. So to make this very simplistic, it's very close to the idea of the t-distribution. So all chi-square values, which is this symbol, are greater than or equal to 0. So the chi-square distribution is a family of curves, each determined by the degrees of freedom. So to form a confidence interval for the variance, we use the chi-square distribution with the degrees of freedom equal to 1 less than the sample size. So we know that the degrees of freedom are going to be n minus 1. So, and the area under the curve of the chi-square distribution equals to 1. So that is also very good to know, because so the area under the curve, so that means a probability which is going to be equal to 100%, right? So, or equal to 1. So that's the idea of the chi-square distribution. This is degrees of freedom 2. So the sample size is 3. So we have a curve that comes down very fast. Then with 5, it's taking more. So go up and down, like kind of resembling a little the normal distribution. So the more degrees of freedom, the more likely this chi-square distribution is going to be similar to the normal distribution. So chi-square distributions are positively skewed. So that means that the tail elongates to the right more than otherwise. So this is the idea. We have a chi-square distribution. So let me make a little map of this, because chi-square distributions are very interesting. So it starts from 0, increases, and then this tail is like this, right? So that's how we present the chi-square distribution. So let me go back to this. So this is what we know. So there are 2 critical values for each level of confidence in the chi-square distribution. We have the chi-square right, and we have the chi-square left. That's when things come a little bit critical, because, okay, we have the chi-square left, and we have the chi-square right. Okay, so those are the values that we're gonna estimate, right? So so we have the chi-square right, the values of the chi-square right represents the right tail of the critical value, and the chi-square left represents the left tail of the critical value. So so in this case, once again, if we want to know the values of the chi-square, we need 2 different things. We need the level of significance, and we need the degrees of freedom, right? So in this case, to find the critical values for chi-square right and chi-square left at the 95% confidence level interval, when the sample size is 18. For example, in this case, if the sample size is 18, the degrees of freedom is going to be 17. Remember, it's n minus 1. So each area in the table represents the region under the chi-square curve to the right of the critical value, right? So so the area to the right of the chi-square right is going to be defined by 1 minus the degrees of freedom, sorry, 1 minus the confidence level divided by 2. So in this case, that's what I don't like too much, because now my chi-square right, so where do we have these values? So so we have two different values. The chi-square right is going to be 1 minus the confidence level divided by 2. So if this is 1 minus 0.95, this is going to be 0.05 divided by 2 is 0.025, right? So the area to the right of the chi-square left, so it's going to be 1 plus c divided by 2. So we are going to use this formula, 1 plus the confidence level divided by 2. So the 2 critical values that we are going to be looking at the table is going to be determined by this, right? So on the one side, to determine the area to the right of the chi-square right, so we are going to use 1 minus the confidence level by 2, and to determine the area to the right of the chi-square left, So we are gonna use the 1 plus level of significance divided by 2. It sounds like a tongue twister. Is the same as, well, that probably might be, I don't think that that is the case, or that might be the case, Terry. I always get confused with all these things. That the reason for me Excel is helpful, because all you need to do in the next part is just to find the values that we need. But if you don't have a computer and you have your tables, so you have to be very careful. Not very careful. You have to be very mindful of what are the values that you are finding, because so on the one hand we are finding the critical values to the chi-square right. So remember, the chi-square right is here, and this is the chi-square left. So we are going to be looking for values here when this is 0.975. This is the chi-square left, and this is going to be 0.025, right? So that's basically, so it's kind of confusing. I don't pay too much attention on this, because when you use Excel, you are going to see what I mean by that. So that's the point. So we are going to use the chi-square left and the chi-square right. So if we are using the chi-square left, so we are using the 9.75, as you can see. So we are going to get a smaller value. When we are using the chi-square right, so we are using the 0.025, so we are getting a higher value. So that's when I said it looks like a little tongue twister here, but just follow this, because the formula is very simple. So in order to find the confidence interval for the variance, so we are gonna use the formula that we described before. So we have the we have well, this is a modified, because now we are going to solve for the variance. So this is going to be the degrees of freedom that multiplies the sample variance and divides the chi-square right. That makes sense, because if we are using the chi-square right, so we are dividing by a big number. We are using the chi-square left on the other side. So in order to find the left endpoint, we are going to divide by the chi-square right. In order to find the right endpoint, we are going to divide by the chi-square left. So is that a tongue twister? I don't know, but so based on the values, so we have to proceed as follows. So we are going to use this as the chi-square left. This is going to be the chi-square right. So when we are solving for this, we are using for the left endpoint the chi-square right, and for the right endpoint the chi-square left. So if we want to find the values, once we find these values, we just take the square root and we find the confidence interval for the standard deviation. So the probability that the confidence interval contain the variance, or the population variance, or the population standard deviation is C, right? So the confidence level. So those are the steps: verify that the population has a normal distribution, identify the degrees of freedom, then find the point estimates. If we don't have the variance of this sample, we have to find it. We know how to find it. Remember, for samples, we say n-1. So we find the square of the deviations. We add all of them up and then divide it by sorry, we square them and then divide it by n-1. So we find the critical values. So once we have the level of significance and the degrees of freedom, we find the chi-square right, chi-square left, and then we proceed with our formulas. So remember, this is the values that we're gonna obtain. So this is the variance, and this is the standard deviation, right? So very simple. It looks like not very simple when we are doing it, but you are randomly selected. You randomly select a weight of 30 samples of an allergy medicine, So you are looking at allergy medicines, you find 30 samples of that medicine. So you know that the standard deviation of this is going to be 1.2 milligrams. Probably if you have the data of the 30 samples, the mean, and then you can find the standard deviation. So in this case, why we are using standard deviations? Just imagine, I think we mentioned that before, that grades at Lehman College and Baruch College are the same. So students are getting a 3.5 GPA. So we can say, well, the mean value is the same. But when you look at what happened in Baruch, probably the data is more compact. So there is less variation than the one that you can find at Lehman. So you might be puzzled why this is happening. So you want to test your standard deviation or your variance. So many cases also when you are producing things, and let's say you are producing bulbs, and you know that every the mean value of production is 100,000 bulbs, and then you know that the standard deviation of this production is something, right? So you can try this, you can test that. So, some of the quality assurance programs pay more attention in the variance rather in the mean values. So in many cases for health, also the variance is more important. You have a medicine that works very fine, and then you find that variation across different groups are more important than the means. So that is a case where you can use the variance of the standard deviation. So in this case, so here we have a sample of 30 people, right? So we are testing this medicine or so you select and weight 30 samples. So you are weighting samples. So you use 30 samples. So the standard deviation, of course, this is the point estimate of your sample is 1.2. So we know that this is the sample standard deviation. And then we assume that the weights are normally distributed. So we need a confidence level of 99%. So does it sound good? Yeah, of course it does sound good, because medications, as we know, I'm not gonna set a 90% confidence interval. Can you imagine if this medication is very strong and people can die? So I want to be very accurate, and 99% sounds very reasonable for this type of research. In some cases, you can even use a 99.9%. So you are sure at the 0.1% level of significance, which is very high. So once again, based on our sample size, we find the degrees of freedom, right? So we have 29 degrees of freedom, and then we are gonna solve it. So we are gonna find the area to the right of the chi-square, right? So we have 1 minus C is 1 minus 0.99 divided by 2. So the value that I'm gonna find in the table is gonna be 0.005. And then on the other hand, I'm gonna find the area to the right of the chi-square left. So I'm gonna add 1 plus 0.99 divided by 2. So I'm gonna use the 0.995, right? So you go to the tables and you find these critical values. So remember, you're gonna use the chi-square right to compute the left endpoint, and you're gonna use the chi-square left to compute the right endpoint. So it makes sense. You are using a big number. You're gonna use a small. You are gonna get a small number. You use here a small number. You're gonna get a bigger number. So you have the right and the left. So as you can see, the math is almost nothing. So we have this right endpoint and left endpoint and right endpoint. So we can say that with 99% confidence, you can say that the population variance is between 80 and 3.18. So once again, do you know the population variance? No, I don't. All I know that with 99% confidence, I can tell you that my population variance is between 0.8 and 0.318. So if I want to find the standard deviation, I just take the square root of this and I compute the values. So I just take if I already have the values, I don't have to do anything else. I just take the standard deviation, the square root, or I can compute the thing again, but I don't have to. I just take the square root, right? So, so what I did here in my Excel file is very simple. I don't want to take credit for something that I probably didn't do. I don't remember. I don't think I am that smart. Probably I found it somewhere in the internet. So if you go to this case, so we have values for the standard deviation. We are going to find the values for the variance. So all I need to compute these values is going to be very simple. I need alpha. So in this case, I have a level of significance. What should I do? So in this case, I said we have to point 1 minus my level of significance. In this case, sorry, a confidence level. So alpha is going to be known as the level of significance, and alpha is going to be found by subtracting the level of confidence minus 1, right? So my level of confidence here, my confidence level is 0.99. So as you can see, I'm going to find the lower alpha and the upper alpha, right? So 0.99. So as you can see, I found the 0.005 and the 0.995. So we have the values to compute. So if you can see here, so I have the formula. So I have the square root of degrees of freedom divided by the chi-square inverse. So I am finding the value for the chi-square given the degrees of freedom. So the formula is very simple. So all I need here, once again, is my sample size, which is 30. And as you can see here, you are going to see the degrees of freedom. And all I need to input again is the standard deviation. If I do 1.2, so I'm going to find the values for the lower and the upper limit of the variance of the standard deviation and the variance. So as you can see here, we have the values that we found. So of course, here I don't know the critical values. We can find the critical values. I will show you how to find them in the next class. So we also have the hypothesis testing, which is a little bit more intense than this. So here we have so the values for the standard deviations, the values for the variance. So let's use 2 decimals. These people are using 2 decimals, and so we have as the standard deviation. Sorry. So the variance is 0.80 and this is 3.18. Of course, if I am writing my results, I'm going to say with 99% confidence, you can say that the population variance is between 0.8 and 3.18, right? So I also can say with 99% confidence, we can say that the population standard deviation is between the standard 0.89 and 1.70 0.89 and 1.78, right? So so that's basically what we did. So you can have any case, any problem, and all you need is alpha. In this case, once again, it's going to be 1 minus c, and automatically we have these values that are going to be computed in this formula. Okay, so and as you can see that the formula next to it is just the square root. So I found the standard deviation, and I know that if I have the standard deviation and I want to convert these values to the variance, I just have to raise to the power of 2 these values, and I will have the variance. Okay, so I think that's it that I have for you today. Is there any question? One
Professor,
question. Yes.
I have a question about the homework as well as
Yes.
um you give us 10 questions, right?
I gave you 10 questions. For 10 questions? For what?
For sapling.
Oh, okay. For the exam or for the
homework.
For the homework. Okay. So what may be the question in that case?
One of the questions is proving a rail nut to crack. Would you be able to help me look over and explain it to me after class?
Yes, sure, of course. Or so let me see. So which example, which exercise is this?
I think it was the proportion was 213 in the hospital in Wisconsin out of 390 with a 2,321 population, and it was like a problem set.
And you said is question number 10.
Estimate the population.
Oh, you already saw the. So according to the current population report in the United States Census, 26% of the people age 65 and older have earned a bachelor's degree or higher. Okay. So suppose that Nancy works at the city of Peoria, Arizona. City officials have asked her to estimate the proportion of people age 65 and older in Peoria who have earned bachelor's degree or higher. They have requested to estimate a confidence level of 90% and a margin of error of 3%, right? So so we have this formula for let me go back. So basically what you have here is what they are asking you for, right? So here you have a confidence level. Hold on, let me make it smaller. So we have this, right? So here, so we have the P, this is P, right? So, hold on. It's very hard to do this with very small screen. I have a bigger screen. I'm actually watching TV by the time I am teaching the class, as you can see. So I get inspired by this. So in this case, we have the P. So the P hat, which is the population, the sample proportion Well, this is the population proportion. That's a very good point. According to the current population, well, you have a P in this case. So I would use the P, hold on. I use the P to compute these values, P and Q. And then I have the level of significance, the confidence level. So this is the confidence level, 90%. And I have the margin of error. So all I need to find is the C-score. So, and you know that you can find the C-score based on this, on the 90%. Hold on, we might need some more information. So according to the current population, I 26.7%. So let me see what, hold on, just give me 1 second. Let me check something. So this is question number 8, chapter 8. No, I was looking for some. So let me see the feedback here. So there are 2 minimum sample sizes. One of the formulas will compute the minimum sample size of the population mean, but this is not the population mean. The other will compute the minimum sample size to estimate a population proportion. That's the hint that you get, right? So let me see my own.
Professor.
Yes, sir.
I'm looking to the same, but I have the different value. That's
which one? Oh, yeah. So that happens very often.
Oh, okay. Yeah, just.
So
okay,
how
this. Yeah,
so,
this. I think. Yeah, this is the.
Yeah, this is the one that you have.
Yeah.
So did you do this example already?
No, I just opened right now.
So let me take a look at this, because I know that we have the confidence level. We need to find the C-score. So so in this case, you have previous information that this is 36% or 20-something%. So you can use this to estimate this P. So and then based on this, you have the Q, right? So which is 1 minus P hat, right? So you have half of your information here. So all you need to find is the so because this is proportions, it's very easy. The 95%, you find the C-score based on the 95%. So so you have so you have the confidence level. So let me go back to my. So in order to find, ay Dios mío. So let me close some of the things here and save. So
I think we just apply the formula because we have already everything.
Yeah, so
we have alpha, we have the error.
Yes, exactly. Hold on.
P and Q and Q.
Now I cannot find. So we have here, so we have the margin of error, right?
Yeah.
So we have the level of confidence. So all we need to find is the C. So in this case, because we are using, so this is the same, so level of the same C-score, 1.96. So in your case is 95%, yes. So so the 95% corresponds to the 1.96. so we can find the value. I was trying to access my I dislike working with a very small computer. But anyways, that's what I get. So what I was looking for is how to find the C-score. This is another class. I just know what I'm doing. So now that. So what we have to do is to find, I mean, if you have a 90% confidence level, so you can use some of the Excel, some of the Excel functions that we know, right? So in this case, 95% corresponds to 1.96. So, so in this case, we can compute this. We have the P, the Q, we have the C-score, and we have the margin of error. That will give you the value that you are looking for. So in this case, so in this case, 31%, 36.1 is the P. Q is going to be 1 minus this. So we have the 90% level of confidence that translate into a 1.96, and then the margin of error. So that is going to give you the sample size. Okay. Who asked this question?
It was me.
Oh, okay. So yeah, that's so that's the way I will do it. So we have P, we find Q, we have the 95%, and we have the margin of error. So you compute those and you will find the sample size. Is that clear or not very clear?
I tried using the Excel formula that you had prepared and things like that, and above all this was only those 3 questions that are left.
Okay, hold on.
And I don't know exactly. Maybe I'm misunderstanding what's going on, but
I don't think. I mean, there is not too much to understand. So just give me 1 second. So let me open this. I have another Excel here. So let me see. Is this is 0.361 times 1 minus 0.361, and then so let me see the formula. Where is the formula? Times open parentheses 1.96 divided by 0.03, and that is squared. This is to the power of 2. So
I got the answer, Professor. That's right.
Is that the answer?
Mm-hmm. Yeah, if you apply the formula.
Mm-hmm. So yeah. So for this, you can get the if you use that formula, so you are gonna find the value for this exercise. I cannot tell you the value, but this is basically what you are gonna do. So and how do you know that this is the right tool? So once again, it's asking you for a proportion. This is a proportion. This is not the mean value. So that means that this is P hat or P in this case. Census means population. So you are trying to find what might be the best, the more, so the best number that you can use, the best sample size that you can use. So all you can do is to use these values and compute the values. If you didn't know these values, some people say, oh, I know that people in Arizona, I don't know how many people who are 60 years old are gonna be 65 and older, or population 24 to 34. That's another case. So I don't know how many. So you can use the 50 and 50, but in this case, you have the probability of success. So so I hope that helps. I don't know if I answered your question. Terry, were you the person who asked the question?
No, it's
Hello?
goodness.
Ah, oh goodness. So use the formula. Use the formula because I think so that's gonna be the value. So multiply P times Q and then P times Q and then multiply it by the C score divided by the margin of error and then squared. And you will find the value. Do it. If you don't get the right result, send me an email and I will check what you did. And I mean, I'll give you the credit for that, but I want you to solve it using the formula. Something that you need to know is that, so in some cases, for example, what I would do with this. So, so the formula is, so let me do this here. So the formula is P hat, let's say, Q hat. We need Z, and we need the margin of error, which is C, right? So so here we have a 0.361, right? Here we have 1 minus 0.361, right? So this is my P, this is my Q, this is my C. If I have the 90%, so let me the norm, that is that IMB. So I have the 0.95. So I think the 95% confidence, and we have, oh, sorry, but this is the 0.975.
Yeah, no, you have to, yeah, the 97th percentile.
Yeah.
97.5 percentile.
Yeah, it's the 196, and then the margin of error 0.03. So you put your formula. Remember, you are gonna do, I will open parentheses. So let me do it without parentheses, without the equal sign, because I'm gonna write the formula. So I'm gonna use P times Q, and then that is gonna multiply the C score, is gonna divide the margin of error, and it's gonna be squared. That's how I would write the question. If you, so of course you have to put the numbers there, but so you have to say P times Q, then times this. Is exactly the formula that we are doing. So we are using parentheses because I mean it's much better for me. I never get lost with the parentheses. So it's kind of solving pieces by pieces. So I will type the formula in that way, and then so of course once again I would say equal. I want to say equal. I'm gonna use the P times the Q times blah 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 blah, right? So and you will do the numbers here. So that's what is gonna be the value. So the sample size here is gonna be determined by this formula. Okay.
Is gonna be 0.02, Professor, I think.
Say that again. Oh, 0.202.
Yeah.
I always get, so yeah. Oh.
Yeah.
0.02. Hold on. I use a 0.02 here. Okay. Yeah. So even like a 2%, I type the formula in another computer. So I use a 3%, and the sample size was very small. I used the 2%, and the sample size went way up. So even a 1% difference in your sample size can make a big difference in your computation of the sample size. Okay, So you guys do the exercise, and if you get the wrong result, just send me an email, show me what you did, and I will do something, okay?
Okay, Professor.
Oh, so let me stop because sometimes we don't need too much.